will do the second synthesis of pyridines. Okay? In this second synthesis, the requirements for the pyridine is that in position 2 and 4 we have electron withdrawing group. Okay, this electron withdrawing group could be an ester, could be a ketone, could be a nitro. The only important is that it's an electron withdrawing group. Okay, I will put esters because it's the most common way, what is called the Handchester, but can be adapted for ketones, nitros, etc. Which is the first step of the retrosynthesis? As usual with pyridine, the first step is to the reduction of the pyridine to a dihydropynide. Okay. Okay, and when we have the dihydropyridine, what we can do is we can take care that this is, we can take a look that this is an enamine and this is an enamine, isn't it? That means that we can break this, and what we can do is this is coming from this amino and this carbonyl group. You can do it in each part, in this part or in the other part. We will see that there are no difference in any of those parts. When we have this, we can take a look that this, we can break this bond. Okay, if we break this bond, okay, we can break this bond, we can put here a positive charge. Okay, this is clearly coming from alpha-beta unsaturated ketoester. Yeah. While the other part is basically this nucleophile. And this nucleophile basically is, here we have an enamine. That means that this is coming from the ketoester plus amino. Okay? And this is coming from the ketoester plus the plus an aldehyde. This is a Novenagel reaction. Okay? This is the common synthesis of the Handchester synthesis. I will put the mechanism, the mechanisms and the forward synthesis. Okay? synthesis, and now I will put the forward synthesis and the mechanism. Basically, the Handchester synthesis is we put all together. Okay, I will do it, for example, with this compound. And benzaldehyde. Okay, in ammonia, basically we mix these three things together, but basically what we do is we put ammonium acetate, okay, because we need acid media, and the first step is the formation formation of the noble adduct. Okay, when we have the noble adduct, what is happening is that basically another molecule of the ketoester will react with ammonium acetate. And what is happening is that basically we form the imine first, and then obviously this is coming to the enamine, this is forming the enamine, and remember that I explained this in the case of pyrroles. When we have a ketoester, the enamine that we form is always with the most acidic proton, that means the internal enamine, because this position is more nucleophilic, well, the hydrogen that was in this position is more acidic, thanks to the presence of the ester. When we have this, basically, this is reacting with the noble adduct that we prepared before. Basically what we have is this compound. Okay, we have this compound. Then tautomerization, imine enamine, and what we get is okay, we get this intermediate, and then basically we protonate the carbonyl compound, and the imine is doing an enamine. And again, I am without a space. And what we will form is this compound that tautomerization imine enamine, the only other form is the enamine between this nitrogen, the imine, sorry, between this nitrogen and this carbonyl group, and now I tautomerize to get the dihydropynide. Okay? Once I have the dihydropyridine, I have to oxidize, and as before, I can use air. Okay. Basically, this is very easy to oxidize with oxygen, or a can to obtain the final compound. Okay? This is how it works if we are using the same ketoester for all the synthesis. That means we mix all together and we get the final compound. What happens if we want to have a pyridine that is different side by side? That means, for example, we want what happens if we want something that is different side by side? The only that we need to do is do it step by step. First, we take, remember how we break the molecule? We need to prepare the novenaryl product. For example, I will prepare the novenaryl product from here. I start with I add the benzaldehyde, piperidine, and pyridine, okay, and normal novenaryl conditions. And what I get is the addition and elimination to get the novenaryl adduct. And then what I do is to add this novenaryl adduct to the other ketoester in ammonium acetate to generate the pyridine. Well, in theory, the dihydropyridine with two different sites, okay, and then I oxidize with air or with can to get the final pyridine. Okay? That means I can do it if both sides of the pyridine are exactly the same. I can do it all in one. That means I add the ketoester, I add the aldehyde, I add the ammonium acetate, that's all. I mix all together, I get the final pyridine. If both sides are different, I have to prepare expressly the novenaryl adduct and then add the other ketoester with ammonium acetate to the novenaryl adduct to get the final product, following exactly the same mechanism that I did before. Okay? This is how we synthesize pyridine. There are only these two types. Well, there are more syntheses, but these are the ones that we will study this year. Formally, 1,5-decarbonyl compounds. How we can synthesize a 1,5-decarbonyl compound? Basically by the Michael addition of an enolate to a alpha-beta unsaturated ketone or ester or aldehyde. Okay. Second option is when we have electron withdrawing groups in the 2 and 4 positions, then what we need to do is to do a Handchester synthesis, basically starting with the ketoester, okay, and an aldehyde, first novenaryl, and then we add another molecule of the ketoester that could be the same or could be different, with ammonium acetate to have the final pyridine. Thank you for your attention and see you in the next lecture.